This is the third video about the false position method for continuous function. So as always, let's start with a function. In this case, we are still gonna start with the very first, with the very same function I started with last time. So x to the third minus 2 equal to 0. But which was, this one, the one of the former video. But this time, I'm gonna start with two different starting point because what I wanna show you is that in a way or another, even if I take a different starting point, eventually, as long as those two starting points are gonna be one negative and one gonna give me one negative value and one positive value, once I plug them into the function, I'm gonna get closer to my solution. So this is going to be our f of x, and my new value this time for x1 and x2, my new values are actually going to be, whoops, well, 0, and x2 is going to be 2. Okay, so basically if I plug them into my function, I get f of 0. So basically 0 to the third minus 2, which gives me 0 minus 2, so negative 2. So the first value is negative, so it's fine. We expect it to get it positive from f of 2. So if I plug back 2 into my function, I get 2 to the third minus 2 equal to 0. Well, equal to 0 equal to something, which gives me 8 minus 2, so 6. Okay, so basically I get a negative value and a positive value. So we're good, because it means that there must be, if the function is continuous, there must be a point in which is going to intersect the axis. So this is 0, which is my starting point, and I get 2 here as my other point. So at 0, the function is negative 2, so like here. And at 2, the function is positive 6, so it's here. So there must be a point in between these interval in which the function is gonna cross the axis. So I'm gonna write the formula once again. So for the false position method, we have x of r equal to x2 times f of x1 minus x1 times f of x2. Everything over f of x1 minus f of x2. There we go. So basically what the formula says once again is that f of x r1, and I get x2, so x2 is going to be 2, my x2, so 2 times the value of x1 in the function x, so x1 was 0, its value was negative 2, so times negative 2, minus x1, which was 0, times f of x2, so 6. Everything over f of x1, so negative 2, minus f of x2, so 6. There we go. So basically, if we compute this, we basically get negative 4 minus 0 over negative 8, which gives us negative 4 over negative 8, which is the same as saying 4 over 8, which simplifies as 1 over 2, which is 0.5. Okay, so basically if we plug 0.5, well, 0.5 is the new value, so we get 0.5, which is like here. So if we plug 0.5 back into our function, let's see what we get. Are we gonna get a negative value or a positive value? Well, f of 0.5 is gonna be 0.5 cubed minus 2, so 0.125 minus 2 equal to negative 1.87. So we still get negative 1.87, which is still negative. Therefore, we expect the function not to cross between 0 and 0.5, but to cross between 0.5 and 2. So we go on with xr2, and we are going to use this new interval. So xr2 is going to be x2, so it's still going to be 2, so 2 times f of x1, so negative 1.87, minus x1, so 0.5, times x2, f of x2, so 6. Everything over f of x1 minus f of x2, so f of x1 negative 1.87 minus f of x2, so 6. Ah, shit. I'm sorry. Sorry about that. Alright, so if we compute this, we get negative 3.74 minus 3 over negative 7.87, which is negative 6.74 over negative 7.87, which is like saying 6.74 over 7.87, which gives us 0.85. So we are now gonna plug 0.85 back into our function and see whether we're gonna get a negative or a positive value. So f of 0.85 is gonna be 0.85 cube minus 2, 0.61 minus 2, so negative 1.38. So it's at 0.85, so like here, 0.85, this is gonna be negative 1.38, so we got here. I'm gonna stop here. So our best guess for this function to intersect is gonna be this graph here. There we go. So this is pretty much like the former example, in which I basically started with a very same function, but I used a different starting point. So I used 0.5 and 2. So as you can basically see, since I started from 0.5, I got 0.85 once again. And then I've been going on and I got 1.06 and so on. In this case, I eventually got the very same value, so 0.5 and then 0.85 and so on. If I was going to go on in this very example here, I would have got as a next value, I would have got precisely 1.06, like in the other example. So, you know, you can start using two different starting points, but you know the important thing is that one of them has to be once you plug them back into the function, one of them has to output a negative value, and the other one has to output a positive value. So the trick here, in order for it to converge faster, is to get two values that are going to get a negative value and a positive value, but you have to try to find them as close as possible. So for example, in this case I got -2 and 6, which is fine because one is negative and one is positive, but you know, getting -1.87 and 6 is way better, because you know they're closer. You know, -1.86 is closer to 0 than -2. So starting with x1 as 0.5 and x2 as 2 is actually better than starting with x1 as 0 and x2 as 2 in this very case. But you know, doesn't really matter. You can go on and do, you know, in this case, one more computation and get where you would have got with these other two starting point. So it's the same. Right, I'm gonna post one more video about the false position method anyway. So stay tuned. Bye for now.